Hello there. I'm so glad we could find this gentle moment together, just as the day begins to fold itself away. Wherever you are, allow the quiet to settle around you like a soft, heavy blanket. Tonight, we're not looking at the stars that twinkle, but turning our mind's eye towards something much more peculiar. A place where the very laws of physics seem to twist and bend into the impossible. We're going to drift toward the last breath of giant stars, where their massive cores collapse into the densest, strangest objects in the entire cosmos. These are worlds made only of the tightly packed remnants of atoms, forming an incredible, silent mystery in the dark. You might think you know what a star is, but tonight, we'll discover how the universe can surprise us, holding wonders that are far more unusual and profound than our quiet imaginations first allowed. It's a vast, dizzying idea, but we'll explore it slowly, like watching a distant light travel its long journey to our planet. If this gentle kind of wandering helps your mind settle or your thoughts quiet, consider a soft like and a gentle subscribe. It helps these stories find other quiet souls looking for a calm harbor in the night. For now, let's simply begin. The strange cosmos is waiting, and we'll take our time. Not so long ago, in 2022, a group of astronomers were quietly watching the sky with a radio telescope in the Australian outback, the Murchison Wide Field Array. They were used to hearing the universe in radio waves, used to the soft, regular ticking of known objects. But in the middle of all that familiar cosmic background, they noticed something odd, a signal that seemed to appear, fade, then return again every 22 minutes. Repeating radio signals are not unusual by themselves. Many of them come from pulsars, those small, dense stellar remnants that spin and sweep beams of radiation across space like lighthouses. As they turn, their beams cross Earth, and we see them as pulses of light or radio waves. That pattern is something astronomers know well. But this signal felt different. When they searched through old observations, they discovered that it hadn't just started in 2022. It had been quietly arriving at Earth since at least 1988. More than 3 decades earlier. Over all those years, through changes in equipment, people, and even the world itself, this distant source had kept to its rhythm with a steadiness that was almost unsettling. If it was a neutron star, it was not behaving like the ones they thought they understood. The source was given a name, as these things often are, GPMJ 1839-10. That label might feel cold and distant, but behind it lies something about 18,000 light-years away in the plane of our galaxy. The light we receive from it began its journey long before many of us were born, traveling all that way just to tap gently at our telescopes every so often. Its signal doesn't arrive as a sharp, neat tick. Instead, each time it appears, it can last anywhere from about 30 seconds to 5 minutes. And each new pulse doesn't always show up at the exact same moment. It has a little window, a band of time just over 6.5 minutes wide, centered around about 22 minutes after the previous one. Somewhere in that window, the next pulse will rise. From our everyday perspective, that might sound messy. 30 seconds and 5 minutes feel very different. A 6-minute variation in arrival time doesn't sound like the work of a precise cosmic clock. But the interior life of a neutron star is complicated. Magnetic fields twist and shift, particle streams brighten and dim, and all kinds of subtle effects can stretch or shrink the pulses we see. So rather than focusing on any single flash, the astronomers took a step back and looked at the pattern over many years. They gathered data from radio telescopes going back 35 years. With all that history laid side by side, they could smooth out the small fluctuations and see the underlying rhythm. From this quiet averaging, a number emerged. The source seemed to be rotating once every 21 minutes and 58 seconds. That's an incredibly slow spin for a pulsar, which usually whirl around many times per second, or at least once every few seconds. Then came the part that made them truly pause. Neutron stars are expected to slow down over time. As they radiate energy into space, they gradually lose rotational speed, like a spinning top that very slowly tires. With 35 years of observations, the astronomers should have been able to measure at least a tiny change in the period. But when they ran the numbers, they found that the spin had stayed, for all practical purposes, exactly the same. If the star has slowed at all, its rotation period has not increased by more than about 0.28 thousandths of a second across all those decades. That is a vanishingly small change for such a slow rotator. It suggests that whatever this object is, it spins with an almost eerie stability, like a clock that refuses to age. The strange thing is that stability by itself is not surprising for pulsars. Many of them are so regular that we use them as cosmic timekeepers, measuring tiny changes in their arrival times to study phenomena across the universe. But those good clocks are normally fast-spinning neutron stars. For one that turns only once every 22 minutes to be this steady is deeply unusual. Something about it does not fit the picture that astronomers have drawn over years of studying these remnants of dead stars. To understand why, it helps to sit for a moment with what a pulsar actually is. Imagine a star many times more massive than our Sun reaching the end of its life. It swells, burns through its fuel, and then collapses. The outer layers are blown outward in a supernova, while the core is crushed under its own gravity into a tiny dense sphere, a neutron star. Apart from black holes, there is nothing denser that we know of. The matter inside such a star is unlike anything we can touch or build on Earth. Our world, and everything on it, is made of atoms, tiny nuclei surrounded by electrons, and between them, a vast amount of empty space. In a neutron star, that empty space has been squeezed away. Protons and electrons are forced together, forming neutrons packed shoulder to shoulder. It is as if the universe took the solid parts of ordinary matter and pressed them into a single, almost seamless drop. A teaspoon of this material would weigh as much as billions of people combined. A typical neutron star can be a bit more massive than our Sun, yet all of that mass is confined to a sphere only about as wide as a large city. To call it dense hardly captures it. It is more like a piece of collapsed space, a reminder that gravity can push matter into extremes that defy intuition. For reasons we still do not fully understand, this environment also produces magnetic fields of enormous strength. The magnetic field of a neutron star can be trillions of times stronger than Earth's. Imagine all the tiny compasses, all the iron filings in the world, all the magnets on refrigerators everywhere, and then go far beyond that. This field shapes the space around the star, guiding charged particles along invisible lines that stretch outward like threads. That is where the pulsar's light is born. The radio waves and other radiation we detect do not simply leak out of the star like heat from a cooling ember. They are produced by a chain of events that begins with a single particle near the magnetic poles. Picture an electron drifting close to one of those poles. The magnetic field grabs hold and accelerates it along a curved path that hugs one of the field lines. Moving along this curve, the electron emits a very energetic photon, a packet of light whose path is roughly tangent to the magnetic line. This first photon is like the opening note of a much larger song. As this photon travels, the geometry between its direction and the magnetic field changes. When a certain critical angle and energy are reached, the photon can no longer continue as plain light. The field is so intense that the photon effectively cracks, giving up its energy to create a pair of particles, an electron and its antimatter twin, a positron. Where there was only light, there is now matter. These newborn particles are also moving in the magnetic field, and their motion is not perfectly aligned with the field lines. They spiral, and in doing so, they emit new photons of their own, a type of radiation called synchrotron light. Each one of these photons can, under the right conditions, undergo the same transformation, turning into yet another electron-positron pair. The result is a cascade. One electron leads to one photon, which leads to two particles, which lead to more photons, which lead to more pairs, and so on. For a brief moment, near the magnetic pole of the neutron star, there is a kind of storm of light and particles multiplying in all directions permitted by the field. This storm grows until the photons no longer have enough energy to split into pairs. When that happens, the chain reaction slows and stops. What remains is a beam of radiation, shaped by the geometry of the magnetic field and the rotation of the star. Some of those photons escape far into space, streaming outward as a narrow beam. The original electron that started it all continues its journey along the field line, emitting more curvature photons and seeding more cascades as it goes. Each rotation of the neutron star brings this beam sweeping around like a lighthouse. If Earth happens to lie in its path, we see a pulse. From our distance, the underlying violence of the process is hidden. We don't see the particles multiplying or the photons cracking apart. We only notice the gentle rhythm of the radio pulses. Yet, it is that chain reaction, repeating over and over near the magnetic poles, that makes a pulsar bright enough for us to detect from thousands of light years away. In most pulsars we've studied, this whole chain of events is tightly linked to how the star loses energy and slowly winds down. The radiation it sends out steals a little from its spin, and over time the stellar clock ticks more and more slowly. With the strange source GPM J183910, the radiation is clearly there. We've seen its pulses for decades, yet any slowing is almost too small to measure. It's as if this tiny, city-sized remnant has learned to shine with unusual steadiness, without paying the usual cost in rotation. So we're left with an odd portrait, a stellar corpse crushed into extreme density, wrapped in a powerful magnetic field that can turn light into matter and back again, sending out radio pulses every 22 minutes with remarkable regularity for at least 35 years. In some ways, it behaves like the pulsars we know. In other ways, it sits just outside the tidy boxes astronomers have drawn from earlier discoveries. Far away, 18,000 light years from here, whatever this object truly is, keeps turning at its own calm pace, its signals brushing past Earth again and again. If you picture one of those signals being born near the magnetic poles of a neutron star, there's one more gentle twist that helps explain what we actually see. The star isn't a steady lamp pointed in all directions, but a rotating beam, so we don't receive a constant glow. Instead, we catch brief flashes like a lantern being slowly turned in the dark each time that narrow beam sweeps across our line of sight. The star is spinning on one axis, the way Earth rotates once each day, But its magnetic poles, the points where those powerful magnetic field lines emerge, are usually tilted, not lined up with the spin. Our own planet is like this too. The place your compass calls north isn't the exact point that marks Earth's true rotation pole. They're close, but not the same. And that small misalignment changes how the magnetic field reaches out into space. For neutron stars, the misalignment is often much more dramatic. The beams of radiation pour out along the magnetic poles, not from the spin axis itself. So, as the star rotates, those beams sweep through space like the arms of a slow, brilliant lighthouse. They don't shine in all directions at once. They trace out narrow, rotating paths. Far away, if one of those sweeping beams happens to cross our line of sight, we don't see a constant blaze. We see a brief blink each time the beam swings past. One turn, one flash. Another turn, another flash. To us, those flashes become a repeating pulse, and the star becomes a pulsar. For GPMJ 183910, the pulses we detect are not invisible light that our eyes could ever see. They arrive as radio waves, with wavelengths so long that only radio telescopes, listening carefully to the sky, can pick them up. The light from the cascades near the magnetic poles is born with a particular character. All the waves rise and fall together, their peaks and valleys in step, and their electric fields are aligned along a common direction. This is what astronomers call polarization. You can think of it as all the light waves agreeing on how they want to wiggle. In ordinary light, those directions are often random. In pulsar light, they are organized, shaped by the star's magnetic field. That ordered polarization is one of the fingerprints of a neutron star, and it is exactly what is seen in the 22-minute signal. The radio waves arrive not as a chaotic jumble, but as a tidy, polarized beam. There is another small, strange detail hidden in the signal. Within each broad pulse, each long flash that can last tens of seconds to minutes, the polarization sometimes flickers. For stretches that last between about 0.2 of a second and 4 seconds, the direction of polarization abruptly swings by 90 degrees, as if the light rotated from lying along one axis to being perfectly perpendicular, then returned again. These sharp flips are not random noise. They are one more familiar mark of those particle cascades near the poles, the way different paths of emission can briefly dominate and then give way. Pulsars often show these orthogonal jumps in polarization, little pivots that speak of the complex geometry of their magnetic fields and the beams they sculpt. So, piece by piece, the 22-minute source behaves like a pulsar. It sends us radio pulses. Its light is polarized. The polarization sometimes flips in that characteristic right-angle way. If you stopped the story there, it would sound like a simple case, a distant neutron star, spinning and shining in the way many others do. And yet, under all those familiar signatures, there is something that refuses to fit. The rotation is much too slow, and the steadiness of that slow spin is too perfect. In the usual life of a pulsar, shining its powerful beam into space, energy is constantly being carried away. That energy has to come from somewhere, and the place it comes from is the star's rotation. The pulsar spins down, ever so gently, as it radiates. You can think of it like a child's top that is pushing against a thick, invisible wind. The top doesn't stop immediately, but you can feel it losing speed. In neutron star terms, that loss is measured through changes in its rotation period, the time between one pulse and the next. Given enough time and a sensitive enough clock, the pulses drift farther apart as the star slows. There comes a point in this process where the rotation has slowed so much that it can no longer sustain those violent pair production cascades near the poles. The star is still there, still massive and dense, still wrapped in magnetic fields, but it no longer has enough rotational energy to hurl particles into those brilliant showers. The lighthouse beam dims and, eventually, goes dark. Astronomers sometimes call this region in their models the Death Valley of pulsars. If you plot neutron stars on a kind of map with their spin period along one axis and how quickly that period is changing along the other, you can draw a faint band that marks where the radio emission should die away. Above that band, stars are spinning fast enough or losing energy quickly enough to light their beams. Below it, they should be quiet, no longer active as recognizable pulsars. When scientists placed the 22-minute source on that map, they found something startling. Its spin period, one full rotation, every 1,318 seconds, is not just a little slower than the usual pulsars. It is more than 1,000 times slower than many of them, which often spins several times per second, or at least once a second, and the rate at which its period is changing, if it is changing at all, is extremely small. On the diagram, this object sits well below the line where radiating pulsars are expected to live. In other words, if GPMJ 183910 is a neutron star, it should be in the quiet graveyard, long past the point where the pair cascades can run. The lighthouse should be dark. Yet, here we are, clearly detecting its pulses, watching its polarized light flicker in our telescopes. If the star were slowing down more quickly, if its rotation were leaking energy at a rapid rate, its position on the map would rise upward into the region where a strong beam could be powered. That would make sense. A star spinning slowly but losing a great deal of rotational energy might still manage the violent processes needed to light up its poles. But this source appears almost stubbornly stable. Its spin hardly changes at all. It shines as if it's losing energy, but its rotation refuses to show the cost. This contradiction pushed the astronomers to look for other possibilities within the family of neutron stars. One idea was that they might not be dealing with an ordinary pulsar at all, but with a magnetar, a special kind of neutron star, whose magnetic field is even more extreme. Magnetars have fields that can be thousands or tens of thousands of times stronger than those of typical neutron stars. In such intense magnetic conditions, the outer crust of the star, the rigid crystalline layer above its dense interior, is under relentless tension. The magnetic field is constantly trying to twist and rearrange itself, while the slowing rotation gradually changes the star's shape. A rapidly spinning magnetar can bulge slightly around its equator, like a spinning water balloon that's a bit wider at the middle than at the poles. As it loses speed over time, this shape can no longer be held. The crust must shift to a new balance. Sometimes, the crust doesn't adjust gently, it snaps. When that happens, the rearrangement of the magnetic field and the release of built-up stress can trigger a sudden, powerful outburst, a starquake. In a fraction of a second, an enormous amount of energy is flung outward in the form of high-energy light and particles. For a magnetar, this can be a brilliant flare, lighting up the X-ray and gamma-ray sky. One especially famous event, from the magnetar known as SGR, 1806 20 inches, 2004, was so intense that if a similar outburst happened within about 10 light-years of Earth, the flood of energy could seriously damage our planet's biosphere. These are not gentle whispers, but cosmic cracks, moments when a neutron star's surface reminds us how much power is hidden in its crust and fields. It is tempting to imagine that such a violent event might also rekindle or enhance radio emission, briefly lighting the beacon of a star that would otherwise be quiet. If anything could wake a pulsar in the so-called Death Valley, surely a magnetar outburst could. So the team studying GPMJ 183910 asked, could this strange 22-minute signal be the long-lived echo of a magnetar starquake? If the neutron star were a magnetar, perhaps its extraordinary magnetic field could bend the usual rules, making it possible for cascades to operate even at slow rotation, or powering some alternative mechanism for radio emission. That would be an elegant explanation. The object would still be a neutron star, just an unusually magnetic and restless one. But magnetars leave certain marks. Their outbursts are not shy. They blaze in high-energy light, especially in X-rays. When a magnetar's crust snaps and its magnetic field rearranges, X-ray telescopes usually have a chance to see the flare, or at least the fading afterglow. And while the radio behavior of magnetars can be complex and sometimes long-lived, the intense phase of activity linked to a major starquake is not expected to last for decades. The energy of these events is enormous, but it is also finite. It tends to burn out on timescales of years, not generations. When astronomers look toward the location of GPMJ 183910 with X-ray observations, they found nothing that matched the story of an ongoing magnetar outburst. No persistent X-ray brightness stood out at that position, despite the expected distance of around 18,000 light-years. There was no sign of a powerful, continuing storm. Even more troubling for the magnetar idea is the timescale. The signal from this source has been detected in one way or another for at least 35 years. If it were the aftermath of a single starquake or a short series of them, the energy should have faded long ago. The 22-minute pulses are too patient, too enduring, to be explained by a brief, catastrophic event that shook the star's crust and then slowly quieted. So the magnetar hypothesis, tempting as it was, starts to crumble under the weight of what we actually see. There is no strong X-ray glow. There is no believable way for a single starquake to power such steady radio pulses for more than 30 years. Each time we try to file this object under a familiar label, ordinary pulsar, fading neutron star, magnetar afterglow, it quietly slips out of place. It looks like a neutron star in its light, behaves like a pulsar in its polarization, yet lives in a region where pulsars should have fallen silent. It hardly slows at all, and it refuses to flare like a restless magnetar. Somewhere inside this small, dense body, the rules we thought we understood are being bent just enough to unsettle us, while our telescopes keep catching the slow beat of its 22-minute pulse and holding on to a question that won't quite resolve. When all those tidy explanations fall away, the signal itself remains. A calm, repeating flash, like a small, steady question in the dark. If it is not a normal pulsar, and not a magnetar in any usual sense, then what kind of object is sending these unhurried pulses from 18,000 light-years away? And what, exactly, is it trying to tell us about how such stars really work? The team who discovered it began to explore other identities this object might be wearing. One idea was that perhaps it is not a neutron star at all, but a different kind of stellar remnant, a highly magnetic white dwarf. White dwarfs are what is left when stars more like our sun come to the end of their lives. They cast off their outer layers into space and leave behind a hot, dense core roughly the size of Earth. Matter inside them is squeezed, but not all the way into a sea of neutrons. The atoms are still there, just pressed into a much tighter crowd. Because white dwarfs are larger and less compact than neutron stars, they can rotate slowly and remain comfortably stable. A spin period of 22 minutes would not be remarkable for a white dwarf at all. And some of them do carry strong magnetic fields. In principle, an unusually magnetic white dwarf could channel charged particles along its field lines and produce radio waves, sending out beams that sweep around as it turns, a kind of softer echo of a pulsar. On paper, it almost feels like the perfect compromise, an object that can turn gently, keep nearly constant time, and still be capable of radio emission. Such a star would not need to cross the death valley that theory draws for neutron stars, because it is not a neutron star at all. It would have its own path to shining. But the details are stubborn. The one known white dwarf pulsar, a system called AR Scorpii, is far fainter in radio light than the source we are trying to explain. Its emission is about 1,000 times less luminous. To make GPMJ 183910 a white dwarf, we would have to imagine a magnetic field stronger than any we have yet measured in such stars, and a mechanism more efficient at turning that field into radio waves. It is not ruled out, but it demands a leap beyond everything we have seen so far. So the astronomers turn to another possibility. Perhaps the signal does not come from a single compact star, but from the dance between two objects. We know that when a star's magnetic field tangles with that of a nearby planet, the interaction can spark gentle radio emissions. Pairs of brown dwarfs, objects too small to ignite as true stars, too massive to be simple planets, have also been seen murmuring in low-frequency radio waves as they orbit and share their fields. These systems show that magnetism and motion can light up the radio sky in more ways than one. Charged particles spiral along magnetic lines, releasing energy as they go. Yet, when we compare their brightness to that of the 22-minute source, the difference is breathtaking. The star-planet and brown dwarf pairs we know are about 100 million times weaker. To reach the strength of GPMJ 183910, we would need to scale up their power by 8 orders of magnitude without breaking the underlying physics. Little by little, the comfortable options peel away. A normal, slowly rotating pulsar should have slipped past the point where pair cascades can run, leaving it radio quiet. A magnetar outburst should reveal itself in X-rays and fade over years, not persist so calmly for decades. A white dwarf would need a magnetic field beyond anything we have seen. Binary systems can whisper in radio waves, but this object shouts. What remains for now is not a tidy label, but a graceful kind of ignorance. Somewhere in the plane of our galaxy, there is an object that behaves like a pulsar in its polarization and pulsation, but that lives in a region of parameter space where pulsars are not supposed to shine. It keeps astonishingly steady time without the expected slowing. It does not flare in high-energy light. It simply turns, and every 22 minutes or so, its presence brushes against our antennas. It can be tempting to feel uneasy when a story ends here, without a clear what it is. Yet this is exactly the sort of unease that moves astronomy forward. Each time the universe shows us something that does not fit our diagrams, it gently reminds us that the diagrams were only sketches, never the whole landscape. Exoplanets, gamma-ray bursts, quasars, many of the things we now take for granted began as stubborn anomalies in the data. With time and patient attention, those anomalies grew into new branches of understanding. The 22-minute signal feels like the beginning of one of those branches for compact stars. The astronomers who uncovered it suspect it is not alone. The method that brought it to light, sifting through radio observations and looking for long, repeating pulses, could easily find others, if they are there. Our telescopes have already gathered vast archives of data along the Milky Way's midplane. It is entirely possible that more such sources are already recorded, waiting quietly in old observations that no one has yet combed through in quite the right way. As new instruments arrive and analysis techniques improve, we may add new dots to this strange corner of the map. Patterns might begin to emerge, and from those patterns we will start to guess at the engines inside these unlikely lighthouses. Maybe they will point toward a new kind of neutron star magnetosphere, able to sustain radio emission well beyond the traditional deathline. Maybe a hidden population of highly magnetic white dwarfs will reveal itself. Or maybe we will realize that there is a piece of the puzzle missing entirely, something we do not yet have language for. Whatever the final explanation turns out to be, there is a quiet thrill in knowing that these objects are out there, pulsing away in the dark. For at least 35 years, GPMJ 183910 has been sweeping its beam through space, crossing interstellar clouds and empty regions alike, until a tiny fraction of its light happens to fall on a radio array on a remote patch of Earth. Each pulse is both a mystery and a promise. There is more to learn about how matter behaves when it is pushed toward its limits. And once you start thinking about matter at those limits, the mind naturally drifts closer, wondering what such a star would feel like if we could somehow approach it. We will never visit the surface of a neutron star. The gravitational pull and radiation would undo us long before we arrived. But in the safety of imagination, we can linger there for a moment and let its properties unfold. Neutron stars are among the densest things the universe allows, before gravity tips over into a black hole. They are the collapsed cores of massive stars that once shone many times brighter than the Sunday. When such a star exhausts its fuel and explodes as a supernova, its inner core is crushed so tightly that protons and electrons merge into neutrons. What is left is a sphere only about 12 to maybe 30 kilometers across, yet holding up to roughly 2 or 3 times the mass of our Sunday. In everyday matter, atoms are mostly emptiness, a tiny nucleus at the center, clouded by electrons in wide orbits. If you removed all the space between those particles, compressing them until they were shoulder to shoulder, you would approach the densities found in a neutron star. It is difficult even to picture. A spoonful of such material would weigh billions of tons under Earth's gravity, like concentrating the mass of a mountain into something you could balance on your fingertip. With so much mass tucked into such a small volume, the gravity at the surface becomes extraordinary. In normal conversation, we often blur mass and weight, saying, "I weigh 70 kilograms, when we really mean that our mass is 70 kilograms. Mass is how much stuff we are made of. Weight is the pull of gravity on that mass, and it changes depending on where we stand. On a lighter world, you feel lighter. On a heavier one, you are pressed down more strongly. Now, imagine placing that same 70-kilogram body on the surface of a neutron star. There, the gravity is about 200 billion times stronger than Earth's roughly 2 times 10 to the power of 11 inches, more formal terms. To find their weight, you would take their mass and multiply by that enormous factor. The resulting force is beyond any ordinary comparison. It would crush bone, metal, and rock alike. Anything with height or structure would be flattened into an almost perfectly thin layer. You can sense the same intensity by thinking about a short fall on Earth. Stepping down from a height of 1 meter brings you gently to the ground. On a neutron star, dropping from that same 1 meter height would fling you toward the surface until you were moving at about 1,500 kilometers per second when you hit. In a single second, you could cross the distance from one large country to another. Even light feels the pull. Normally, in empty space, light travels in straight lines, but around a neutron star, space-time itself is bent. Light can be forced into tight, looping paths, even into orbit. From the right vantage point, a distant observer could in principle see photons that have skimmed around the far side of the star and come back toward them, making more than half of the surface visible at once. The star is not just sitting in space. It is sculpting the space around it. When you let these numbers sink in, the billions of tons in a spoonful, the 200 billion-fold increase in weight, the 1 meter fall at 1,500 kilometers a second, they begin to feel less like raw data and more like a kind of quiet awe. They are the natural consequences of simple laws applied in extreme conditions. Gravity, quantum mechanics, and the conservation of energy do not change. They are simply pushed into regimes far beyond anything we experience in daily life. Somewhere in that extreme regime, an object like GPMJ 183910 is turning. Whether it is a neutron star, an unusually magnetic white dwarf, or something we have not yet named, it lives in a world where weight, density, and curvature take on values that feel almost unreal from our gentle vantage point on Earth. From that compact stage, a beam of radio light sweeps outward, crossing the darkness for 18,000 years before it brushes past our planet for a few seconds every 22 minutes. We still don't know exactly what kind of star is doing this, but we know enough to feel the pull of the question itself, to sense that something new waits just beyond the edge of our current theories. To get a sense of how different that world really is, it helps to imagine what standing on such an object would mean. The mind instinctively reaches for something solid underfoot, like a rocky hillside or a concrete floor, but the reality would be nothing like that. In a gravity field hundreds of billions of times stronger than Earth's, a human body would not remain a person in any familiar sense. In the first instant of contact, every part of you would be dragged downward with overwhelming force. Bones, organs, even the empty spaces inside atoms would be crushed together. The tidy structure of ordinary matter would collapse, layer by layer, until what was once a body became part of the star itself, spread into something like a single sheet of particles, a tiny addition to an object already unimaginably dense. This gravity, so fierce, it erases texture, also gives neutron stars another strange distinction. They are likely among the smoothest, most perfect spheres in the universe. Mountains, hills, and valleys as we know them cannot survive there. Even a bump, just a few centimeters high, would contain more mass than the heaviest buildings on Earth, and gravity would relentlessly grind it back down. What remains is almost pure geometry, a nearly flawless ball of matter pressed into shape by its own pull. While we sit on our softer, irregular world, something else is happening out in space that ties back, in a quiet way, to these compact stars. Around 800 light-years from us, there is a region that behaves like a hidden factory of antimatter. It is not a factory in the human sense, no walls, no chimneys, no machines, but a place where the universe itself seems to be generating high-energy positrons, the antimatter partners of electrons. These tiny particles stream out into the galaxy, drifting through magnetic fields and interstellar gas, and some of them eventually find their way to the neighborhood of our planet. For most of our history, this invisible rain was completely unknown. Positrons arriving near Earth were swiftly swallowed by the upper layers of the atmosphere, colliding with electrons, annihilating, and turning into light long before any detector could notice them. It was only when we learned to carry our instruments beyond the air, up into orbit, that we began to glimpse this hidden flux. In 2011, a carefully built experiment called the Alpha Magnetic Spectrometer was switched on aboard the International Space Station, a few hundred kilometers above our heads. It is essentially a very sensitive particle detector, sifting through cosmic rays and sorting out their charges, masses, and energies. Among the many particles passing through it, the instrument found positrons exactly as expected, but not in the expected numbers. The further it reached into higher energies, the more positrons it saw, far more than could be easily explained by the usual sources such as natural radioactive processes or ordinary cosmic rays smashing into interstellar gas. It was as if someone had quietly turned up the dial on antimatter production in our part of the galaxy. Suddenly, the question was not, are there positrons, but why are there so many? Somewhere, something was feeding this surplus, and it was doing so with considerable power. Only in recent years have astronomers begun to trace this excess back to its likely origin, and the trail leads to a familiar kind of high-energy object, a pulsar. Long before we knew about the positron surplus, there was another mystery. In almost the same region of sky, a hazy, persistent glow of gamma rays, the most energetic form of light. In the early 1970 seconds, a small NASA satellite called SAS-2 scanned the Milky Way in gamma rays and found an unusual patch of brightness in the constellation Gemini. The instrument could not pinpoint a precise source. The glow seemed to come from a fairly wide area. The object behind it, whatever it was, remained hidden. Despite this uncertainty, the source was given a nickname that stuck: Geminga. The word folds together Gemini and Gamma, hinting at its position and its type of light. In an Italian dialect, it also sounds like a phrase meaning, "It's not there." A gentle joke about how the object refused to show itself clearly. For years, Geminga was exactly that, present in the data as a blur of high-energy radiation, but elusive whenever astronomers tried to connect it to a specific star or remnant. A small step forward came in 1983, when Giovanni Bignami and his colleagues detected a faint X-ray signal from the same general region using an orbiting X-ray telescope. X-rays are less energetic than gamma rays, but still mark violent processes, and their appearance suggested that Geminga might be associated with a compact object or some kind of energetic environment. Still, its exact identity remained a matter of educated guesses. No clear pattern, no obvious star, just a dim point within a larger haze. The picture began to sharpen in the early 1990 seconds. Two separate space missions, both looking in high-energy bands, caught something new: a regular pulsing in the light from Geminga. One was ROSAT, a German-led X-ray observatory that detected faint, repeating variations in X-ray brightness. The other was EGRET, a gamma-ray instrument aboard the Compton Gamma Ray Observatory, which saw matching pulses in the gamma-ray band. Both sets of pulses arrived with the same period, about 0.237 seconds. In other words, whatever Geminga was, it was flashing a little more than 4 times each second. That rhythm is the signature of rotation, A compact object spinning on its axis is sweeping beams of radiation past us, just as a neutron star does when its magnetic poles are misaligned with its spin. With that discovery, Geminga stepped out of the fog and took on a clearer identity. It was a pulsar, a rapidly rotating neutron star, whose beams happened to be strongest in X-rays and gamma rays. At the time, this made Geminga part of a very small club. Only two other gamma-ray pulsars were firmly known: the Crab pulsar and the Vela pulsar, both famous remnants of supernova explosions. But Geminga differed from those earlier examples in ways that made it even more intriguing. First, Crab and Vela are bright in radio waves as well as in higher energy light. Their lighthouse beams sweep past Earth across a wide range of wavelengths, so radio telescopes can pick them up easily. Geminga, on the other hand, seemed almost completely radio quiet. When astronomers pointed sensitive radio dishes toward its position, they saw nothing like the regular flashes they expected. Here was a neutron star whose presence announced itself in gamma rays and X-rays, but that barely whispered, if at all, in the long radio wavelengths, where most pulsars are first discovered. Second, both Crab and Vela sit at the centers of nebulae, clouds of gas and energetic particles still glowing from the explosions that formed them. These nebulae are like afterimages of the supernova, caught in slow motion, and they help confirm the story of the star's violent birth. Geminga, in contrast, appeared to be alone. There was no obvious shell of glowing gas wrapped around it, no bright remnant marking a recent catastrophe. It looked, instead, like a pulsar drifting through space without its original supernova cloak. These differences raised quiet but persistent questions. Why would one pulsar shine so strongly in gamma rays and yet hide so thoroughly in radio wavelengths? What had happened to its nebula? Had it faded with time, or been too faint to see from the beginning? Was Geminga older than Crab and Vela, far enough along in its life that the explosive debris had thinned and cooled beyond easy detection? Or was something about its environment and magnetic field fundamentally different? As observations improved, Geminga's spin rate, energy output, and distance estimates all came into better focus, and its role in the positron story grew clearer. A neutron star spinning several times per second, funneling particles along its magnetic field lines, can act as an accelerator, boosting electrons and positrons to high energies and flinging them out into the surrounding space. Over hundreds of thousands of years, a nearby pulsar like Geminga can fill a region of the galaxy with these particles. Some of them wander, guided by tangled magnetic fields, toward our solar system, where a small fraction will eventually pass through instruments like the Alpha Magnetic Spectrometer. In that sense, Geminga is not just a curious footnote in the catalogue of neutron stars. It is a bridge between the extreme physics of collapsed stellar cores and the tiny, invisible messengers that brush against our detectors in low Earth orbit. The smooth sphere of a neutron star, the crushing gravity that would flatten any visitor into its surface, the beams of radiation sweeping through space, the distant haze of gamma rays, the excess of positrons at the edge of our atmosphere, all of these are threads of the same story, woven across vast distances and long stretches of time. So when we picture a neutron star now, it is not merely as a silent, abstract object, a dot on a graph, a dense number in a table, but as something actively shaping its surroundings. It bends space-time, sculpts magnetic fields, and becomes a generator of high-energy particles that can cross light years to whisper their presence into our instruments. Some neutron stars pulse quickly, some more slowly. Some glow in radio, some in X-rays and gamma rays, some perhaps in ways we have not yet learned to notice. A few, like the 22-minute enigma and the ghost-like Geminga, sit at the edges of what we think is possible, inviting us to soften our certainty and look again. In the hush of the night, it can be strangely comforting to remember that the cosmos is full of such unseen connections. A particle detected for a fleeting moment above our heads may have begun its journey in the magnetosphere of a star that died long before humans learned to write. A patch of gamma-ray haze in a constellation's outline may turn out to be the echo of a collapsed core, still spinning, still sending out pulses more reliable than any clock we can build. And somewhere, in those pulses, in those showers of light and antimatter, the universe is quietly telling us that there is always more to learn, that every mystery, no matter how distant, is also a gentle invitation to keep listening. For a long time, part of the reason Geminga seemed so ghost-like was simply that we weren't listening in quite the right way. Our telescopes and our theories were tuned to certain notes and certain habits, and Geminga was playing a quieter, lower song just beyond our usual range. Radio pulsars can, in principle, sing across a very wide band of radio frequencies, from tens of megahertz up to tens of gigahertz. But not all of those tones travel through space with equal ease. Between a pulsar and our dishes on Earth lies the interstellar medium, a thin soup of gas and charged particles, as well as the glow of the radio sky itself, and, closest to us, the shifting, restless layer of our own ionosphere. Lower frequency waves, the kind down in the tens or low hundreds of megahertz, are especially vulnerable. They are scattered, absorbed, blurred and softened as they cross this layered path, so that by the time they reach us, they can be far weaker than when they left the star. Astronomers had learned, going back to the 1970 seconds, that many pulsars are actually at their brightest around 1 to 200 megahertz. Yet, because those low frequencies are so easily muffled, most radio searches for pulsars chose to listen higher up, where the atmosphere and the interstellar medium are kinder. Many big surveys concentrated on frequencies between about 400 and 1,600 megahertz, a compromise that works beautifully for most known pulsars. If Geminga had been a typical radio pulsar, that choice would have been fine. Its beam would have cut through at those higher frequencies, and it would have joined the growing catalog of radio sources long before its gamma-ray nature was fully understood. But Geminga was not typical. Its radio voice, if it had one, was faint and low, tucked down closer to the range where our instruments were least comfortable and our searches least thorough. It took until the late 1990 seconds for the picture to change. In 1997, 3 independent observing runs at the Pushchino Radio Astronomy Observatory in Russia used a specially tuned, highly sensitive transit antenna to listen around 100 megahertz, right where pulsars are intrinsically strong, but the journey through space is hardest. In that narrow window, they finally picked up what others had missed: extremely weak, regular radio pulses, matching Geminga's known spin period. It was as if a distant lighthouse that everyone had assumed was dark suddenly revealed a tiny, far-off glimmer once someone dimmed the room and let their eyes adjust. Geminga had been calling out all along. We just hadn't been listening at the right pitch. Around the same time, a team, led by the astronomer Janusz Gill, explored another piece of the puzzle: Geminga's own magnetic environment. Their models suggested that the pulsar's magnetosphere, The cocoon of magnetic field and particles surrounding the star could be swallowing or bending much of its radio emission before it ever had a chance to escape. Higher frequency radio waves, the kind most surveys were tuned to, might be absorbed or refracted inside this magnetic shell, leaving only a fragile whisper near 100 megahertz to leak out into space. Put together, these ideas make Geminga's apparent silence less mysterious. It is not truly a mute pulsar. It is a pulsar whose voice is both muffled at the source and further softened along the way, so that only the most patient, low-frequency listening can catch it. By the time those waves arrive at Earth, they are so faint that they lie at the very edge of what our instruments can see, confirming that Geminga is a pulsar, and more specifically, a gamma-ray pulsar, turned out to be more than a tidy label. It revealed just how extreme this object is. Roughly 99% of the energy it radiates comes out in gamma rays, making it one of the brightest gamma-ray beacons in the entire Milky Way. What we see now is the leftover core of a star several times more massive than our Sun, which exploded as a supernova perhaps 350,000 years ago. The expanding debris has faded into the general background, but the core remains, spinning and shining in high-energy light. Even with that picture in place, Geminga still had more secrets to share. When Italian astrophysicists, including Giovanni Bignami, the scientist who gave Geminga its name, compared images taken years apart, they noticed something subtle but persistent. The faint point of light associated with the pulsar was not in exactly the same place. It had moved. To measure this properly, they combined data from several large optical telescopes, including instruments at the European Southern Observatory and the Canada-France-Hawaii telescope. With careful analysis, they found that Geminga was drifting across the sky at a rate of about 0.2 arcseconds per year. An arcsecond is a very small unit of angle, much smaller than the degrees we use for everyday directions. If you divide a full circle into 360 degrees, and then each degree into 60 arc minutes, and each arc minute into 60 arc seconds, you end up with 1 degree equals 60. Arc minutes equals 3,600 arc seconds. These tiny slices help astronomers describe how stars change their positions over many years as the Sun and its neighbors orbit the center of the galaxy. From the ground, with your own eyes, you won't notice those shifts. Most stars move only a few thousandths of an arcsecond per year, as seen from Earth, a drift so small that it takes precise instruments and long patience to measure. Against that quiet backdrop, 0.2 arcseconds each year is surprisingly fast. It can help to anchor this in something familiar. Imagine drawing a circle in the sky that traces the moon's path around Earth. That circle covers 360 degrees. At any given moment, if nothing blocks your view, you can see about half of that circle, roughly 180 degrees, from horizon to horizon. From the horizon up to the point directly overhead is about 90 degrees. If you stretch out your little finger at arm's length and close one eye, the tip of your finger covers about 1 degree of the sky. The moon itself spans only about half a degree, or roughly 30 arc minutes from one side to the other. Now imagine that very small unit, an arcsecond. There are 60 of them in each arc minute, so it takes 1,800 arcseconds to span the moon's width. Geminga creeps across the sky at just 0.2 arcseconds per year. That means that, from our point of view, it would take a bit over 10,000 years for Geminga to drift by, about 30 arc minutes the apparent diameter of the moon. On human timescales, that motion is invisible. On cosmic timescales, it is a clear sign of a star racing through space. When astronomers translate that tiny angular motion into an actual speed through space, taking into account Geminga's distance of about 800 light-years, they find that this neutron star is traveling at nearly 210 kilometers per second. Every second, it moves farther than the distance between many major cities on Earth. Every minute, it could cross a continent. Yet, because it is so far away, we perceive this headlong rush as a slow, measured crawl across the background stars. Geminga is heading toward the border between the constellations Gemini and Lynx. At its current pace, it will stay within the boundaries of Gemini for another 500,000 years or so, before its path carries it, by our naming of the sky, into a new constellation. The star itself, of course, does not know or care about the lines we draw between patterns of light. It is simply following the trajectory it was given, likely kicked into motion by the asymmetry of the supernova explosion that created it. There is something quietly poetic about this combination of traits. Geminga is almost radio silent, yet blazingly bright in gamma rays. It spins quickly, flashes like a cosmic lighthouse 4 times a second, and still manages to slip through the radio surveys that first defined its kind. It drifts through space at hundreds of kilometers per second, yet we need decades of careful observations to notice its motion at all. In that sense, Geminga sits at an interesting crossroads in our understanding of neutron stars. It reminds us that our instruments hear only part of the cosmic symphony, that some notes are easier to catch than others, and that what looks like silence may simply be sound outside the band we are used to listening in. It also hints at the restless lives of stellar remnants, not fixed, not static, but traveling, spinning, evolving, all while shaping their surroundings with beams of light and clouds of particles. Somewhere out there, other Geminga-like pulsars may be speeding along their own paths, their gamma rays blending into the general glow, their radio whispers just below the frequencies we have most often chosen. As we build new telescopes and tune them differently, lower in frequency, wider in field, more sensitive to the faintest of patterns, we may begin to find them, one by one. Each discovery will add a small, steady note to the larger story of how neutron stars live, move, and quietly light up the galaxy around us. As strange as Geminga already seems, a fast-spinning, nearly radio-silent pulsar racing through space, it has one more secret stitched into its path. Its great speed does not just carry it quietly across the constellations, it sculpts the space behind it. As Geminga hurtles forward, it leaves behind twin traces, 2 faint X-ray tails that stretch for trillions of kilometers, like ghostly brushstrokes following a moving hand. These structures were not obvious at first. For many years, our view of the X-ray sky was simply not sharp or sensitive enough to reveal them. That changed in 1999, when the X-ray multi-mirror mission, better known as XMM Newton, was launched to explore the high-energy universe in more detail, to see the quiet glow of hot gas and the sharp signatures of compact, energetic objects. About 4 years later, a team led by Patrizia Caraveo turned this new eye on Geminga. When they studied the data, they found 2 elongated structures trailing away from the pulsar, like the tails of a comet, glowing softly in X-rays. Each one stretches on the order of 3 trillion kilometers, an almost unimaginable length, drawn out behind a single compact star. Their shape and brightness tell a layered story about motion, matter, and magnetism. As Geminga races through space, it plows into the thin interstellar medium, a gas so tenuous that there may be only a tiny fraction of an atom in every cubic centimeter. To our senses, that would feel like a perfect vacuum, but to a neutron star traveling at hundreds of kilometers per second, it is enough to raise a bow wave, a shock front, where the star's wind and the surrounding material collide. Along this front, Geminga's own magnetic field is squeezed and strengthened. The field lines bunch together, and plasma-charged particles flowing out from the pulsar is compressed and redirected. It is along the edges of this three-dimensional shock that the X-ray tails appear, tracing out the paths along which particles are being guided and accelerated. All of this rests on what Geminga is at its core, a tiny, incredibly dense ball of neutron star matter. Its diameter is only about 20 to 30 kilometers, smaller than a modest city, but it packs in roughly 1.5 times the mass of our Sunday. To get a feeling for that density, you can imagine scooping up a teaspoon of neutron star material. That spoonful would weigh billions of tons, comparable to the mass of tens of thousands of skyscrapers combined. It is matter pressed almost to its limit, neutrons packed so tightly that there is hardly any room left between them. Now, picture that dense object racing through the interstellar medium. Even though the gas it encounters contains only a handful of atoms in volumes that would seem empty to us, the neutron star's enormous mass and speed turn this encounter into a powerful interaction. As it moves, the pulsar compresses the surrounding gas and its own embedded magnetic field by a significant factor, increasing the field's strength and shaping the region through which the particles must travel. At the same time, the star's continuous rotation keeps its magnetosphere busy. Electrons and their antimatter twins, positrons, are constantly being accelerated to extreme energies along the pulsar's magnetic field lines. Many of these particles eventually escape, and their motions and collisions give rise to the high-energy gamma rays for which Geminga is famous. Those gamma rays are the most direct light we see from the pulsar itself, a kind of sharp, high-energy heartbeat. But not every particle flies straight outward and vanishes into the galaxy. Some become trapped, spiraling within the compressed magnetic field in the region around and behind the moving star. As they trace out tight, curved paths at nearly the speed of light, they emit X-rays. It is this radiation that paints the two long tails, visible in XMM Newton's images and in detailed computer simulations, delicate, luminous wakes marking where Geminga has been. If you could somehow see X-rays with your own eyes, Geminga might look like a small, bright coal with twin streaks trailing behind it, the way a fast boat leaves curved waves in a calm lake. The comparison is not perfect, of course. The water here is an almost empty gas, and the wake is made of particles so energetic that they can strip electrons from atoms and shine in X-rays. Still, the overall shape, the forward bow of the shock and the fading, tapered tails feels strangely familiar. For a long time, one more piece of the picture seemed to be missing: a nebula. The Crab and Vela pulsars sit inside bright, swirling clouds of energized gas and particles, leftovers from the explosions that created them. These nebulae are easy to spot and help confirm their identities as young, active neutron stars. Geminga, by contrast, appeared almost solitary, with no obvious surrounding cloud. That absence added to the sense that this pulsar was unusual, that its supernova's imprint had somehow faded into the background without leaving a visible signature. Then, in 2005, another quiet step forward brought the scene into better focus. Observations revealed a shell of neutral hydrogen gas around Geminga, forming a kind of soft, rounded boundary with a radius of a fraction of a parsec a little under a light year across. This shell turned out to be a pulsar wind nebula, a structure created not by the initial explosion but by the continuous outflow of particles from the pulsar over many thousands of years. From the magnetic poles of Geminga, a wind of plasma, electrons, positrons, and other charged particles streams outward at nearly the speed of light. As this wind pushes into the surrounding medium, it hollows out a bubble of high-energy particles and magnetic fields. Within this bubble, the particles spiral and radiate, giving off X-rays and other energetic light. The nebula is like a faint glow in the air around a street lamp on a misty evening, except that here the mist is a blend of interstellar gas and ultra-fast particles, and the lamp is a neutron star turning 4 times a second. With the discovery of this pulsar wind nebula, Geminga's identity as a pulsar felt complete. It had the rapid spin, the gamma-ray pulses, the faint but real radio whispers, the X-ray tails, and now the surrounding cloud of energized material. The pieces, all lined up, a stellar remnant, still active, still shaping its environment with radiation and wind. Yet, astronomers were still curious about why Geminga looks the way it does when compared to other, seemingly similar pulsars. The Chandra X-ray Observatory, with its very sharp vision, helped them look closer. Chandra observed not only Geminga, but also another pulsar, catalogued as B355+54. For simplicity, we can think of it as Pulsar B. At first glance, Geminga and Pulsar B share several important traits. Both are relatively middle-aged for neutron stars, roughly 500,000 years old. Both spin a few times each second, with rotation rates of about 4 to 5 Hertz. Both are neutron stars moving through the galaxy, each with its own magnetic field, its own particle wind, and its own subtle influence on the surrounding gas. But their personalities, when translated into light, could hardly be more different. Geminga shines strongly in gamma rays, producing powerful pulses in that high-energy band and showing up clearly in X-rays, yet it offers only a very faint trace of radio emission. Pulsar B, on the other hand, is one of the brightest radio pulsars in the sky, sending out strong, regular flashes in radio wavelengths, while it remains quiet in gamma rays, with no equally strong high-energy pulses detected. Seen side by side, they pose a gentle question. How can two neutron stars with similar ages and spin rates present such opposite faces to our instruments? What makes one of them a gamma-ray beacon with a radio whisper, and the other a loud radio voice with almost no gamma-ray song at all? Part of the answer may lie in simple orientation, the way each star is tilted relative to us. Pulsar beams are not spheres of light that flood space evenly. They are more like narrow cones or fans, fixed to the star's magnetic poles. As the star spins, those cones sweep through space like rotating spotlights. Whether we see them and which wavelengths we see depends on how those cones cross our line of sight. It may be that Geminga's radio beam is very narrow or strongly absorbed within its magnetosphere, so that only a weak sliver at low frequencies escapes in our direction. Its gamma-ray emission, however, may be spread over a broader region around the magnetic poles, giving Earth a steady view of its high-energy pulses. Pulsar B might be arranged the other way around. Its radio beam points squarely at us, while its gamma-ray emission sweeps somewhere else, missing Earth entirely. In that light, Geminga and Pulsar B stop looking like contradictions and start to resemble two different camera angles on the same kind of object. They remind us that what we perceive is shaped not only by the intrinsic properties of a star, but also by where we happen to be standing in the vast three-dimensional theater of space. A single neutron star can, all at once, be a source of radio flashes, a generator of gamma rays, a sculptor of X-ray tails, and the heart of a pulsar wind nebula. From our small corner of the galaxy, we see only the slices of that complex reality that happen to cross our view. The rest continues, quietly, just beyond the edges of our instrument's sensitivity, unfolding whether or not anyone is there to watch. Sometimes two things can be almost twins on paper, yet look utterly different when you meet them. Geminga and Pulsar B are like that. Both are neutron stars, born in supernovae, a few 100,000 years old, spinning 4 or 5 times each second. Both are plowing through the galaxy with their own winds and wakes. Yet to us, Geminga is a bright gamma-ray lantern with only a faint radio murmur, while Pulsar B is one of the loudest radio voices in the sky, nearly invisible in gamma rays. Astronomers think the difference may be as simple as the way each star is tilted with respect to Earth. A neutron star is a spinning magnet. It has a spin axis, the line around which it rotates, and a magnetic axis, the line connecting its two magnetic poles. Those poles are where the narrow beams of radio emission are focused, a little like Earth's magnetic north sitting not far from its geographic north. You can picture it with a small foam ball, pierced straight through the center by a skewer. The ball is the neutron star. The skewer marks both the spin axis and the direction of the magnetic poles. Around that axis, two cones of radio emission extend outward from the poles. As the ball spins, those cones sweep through space like twin spotlights. Around the middle of the ball lies the spin equator, where the surface moves fastest as the star turns. Now, imagine sliding a thin paper ring around the ball along that equator. That ring stands in for a broader region where gamma rays are produced, a kind of glowing belt encircling the star. The real structure is more complex, but the picture is enough. Tight radio beams near the poles, a wider zone of high-energy emission around the equator. What we see depends on where we are. If our line of sight crosses one of the polar beams, every rotation brings a sharp radio pulse. If instead we intersect the equatorial belt, we see gamma-ray pulses. Sometimes we get both. Sometimes we get only one, simply because the beams miss us. For Geminga, it seems that Earth lies close to the edge of that equatorial gamma-ray band, as though we are looking along the rim of the paper ring. Each spin sweeps that bright belt across our view, so the gamma-ray pulses stand out clearly. But Geminga's radio beams, rooted at the poles, are angled a little to the side. They sweep across the galaxy without ever pointing straight at us, or they do so only weakly, at low frequencies, where the signals are hardest to hear. Pulsar B seems to be arranged the other way around. In this case, we are more like an observer looking face-on at the ring. The strongest gamma-ray emission is spinning mostly across our line of sight instead of through it, slipping past unnoticed. The polar radio beams, however, are tilted so that at least one of them crosses our direction. With every turn of the star, that narrow beam brushes Earth, lighting up our radio telescopes again and again. X-ray images from Chandra give this geometry a more concrete shape. In pictures of Pulsar B, long streaks trail away from the star jets of particles flowing out along the magnetic poles. Because the pulsar itself is moving, those jets bend backward, like streamers caught in a strong wind. In Geminga's portrait, the twin tails flare more to the sides, roughly parallel to the star's motion. That matches the idea that its polar jets and any strong radio beams anchored to them are directed sideways with respect to Earth, while we are better aligned with the equatorial region where gamma rays are produced. In the end, the contrast may not require any exotic new physics. It may simply be a matter of perspective. The same kind of lantern, seen once from the side, once from above. But this gentle shift in angle turns out to matter a great deal for a mystery much closer to home: the strange overabundance of antimatter in the form of positrons drifting past Earth. High above our heads, attached to the International Space Station, a device called the Alpha Magnetic Spectrometer, or AMS-02, has been quietly counting particles for years. Cosmic rays, energetic protons, and fragments of heavier atoms race through space at nearly the speed of light. Mixed into this rain are positrons, the antimatter twins of electrons. When a positron meets an electron, they annihilate, turning their mass into light. By 2013, AMS-02 had recorded more than 400,000 positrons, building the largest sample of such particles ever collected. When scientists plotted how the number of positrons changed with energy, they found something odd. At higher energies, there were far more positrons than simple models of cosmic rays, and their collisions would predict. It was as if an unseen source had been pouring extra antimatter into our corner of the galaxy. For a while, one idea shone particularly brightly. Perhaps these positrons were the signature of dark matter. Dark matter is the invisible mass that seems to outweigh ordinary matter in the universe by roughly 5 to 1. We cannot see it directly, but we see its gravitational fingerprint in the motions of stars and galaxies and in the large-scale web of cosmic structure. Some theories suggest that dark matter is made of particles that, on rare occasions, collide and destroy each other, producing high-energy electrons, positrons, and gamma rays. If that were true, then an excess of positrons near Earth might be the first real clue to dark matter's nature. For years, many physicists let themselves hope that the AMS-02 data were whispering that story. At the same time, a quieter possibility sat nearby. Pulsars are natural factories of electrons and positrons. In the intense magnetic fields around a neutron star, particles are routinely accelerated to extreme speeds. Pair cascades, like the ones that power radio and gamma-ray beams, naturally produce equal amounts of matter and antimatter. Over tens or hundreds of thousands of years, those particles leak out into the surrounding space, forming halos around each pulsar. It had long been suspected that nearby pulsars, Geminga among them, could contribute significantly to the positron excess. But suspicion is not proof. Astronomers needed a way to see whether electrons and positrons streaming away from these stars were actually lighting up their surroundings in the right way. In 2017, a telescope called HALSI, the High Altitude Water Cherenkov Gamma Ray Observatory, added an important clue. HAWK watches for the faint flashes created when very energetic gamma rays hit Earth's atmosphere. And from those flashes, it can reconstruct where the gamma rays came from. With this method, it detected a compact halo of ultra-high energy gamma rays around Geminga and another pulsar. Such gamma rays are exactly what you expect when high-energy electrons and positrons wander through a sea of softer photons and kick those photons up to much higher energies. HAWK's detection was the first clear link between a specific pulsar and this kind of gamma-ray halo, a sign that Geminga was actively filling its surroundings with energetic charged particles. Even so, early interpretations were cautious. The halo HAWK saw seemed relatively compact and bright. Some researchers argued that If particles were diffusing outward so slowly and losing so much energy nearby, very few of Jaminga's positrons would make it as far as Earth. If that were so, Jaminga could not be responsible for the positron excess measured by AMS-02. A few years later, another group took a broader view. Using nearly 10 years of observations from the Fermi Large Area Telescope, which is sensitive to lower energy gamma rays than HARS, they carefully subtracted all known sources of gamma ray emission around Jaminga. What remained was a diffuse, softly glowing halo centered on the pulsar, far larger than the compact patch Hall had highlighted. At energies around 10 billion electron volts, this halo stretched across about 20 degrees of the sky, comparable to the size of the Big Dipper. At lower energies, it appeared even wider. If your eyes could see such gamma rays, Jaminga would not be a tiny point, but a vast, oblong glow, its light spilling across an area many times wider than the full moon. This discovery changed how scientists thought about the particles around Jaminga. A larger gamma ray halo suggests that electrons and positrons are diffusing more freely and over longer distances than some earlier models assumed. When this updated picture was fed into calculations of how many positrons might eventually drift to Earth, the result was striking. Jaminga alone could plausibly account for a significant fraction, perhaps around 20% of the excess positrons detected near our planet. From there, it does not take much imagination to see how a collection of similar pulsars, each with its own halo of energetic particles, could add up to most of the remaining excess, rather than one dramatic, exotic source. We may be looking at the quiet sum of many neutron stars doing what they naturally do, spinning in strong magnetic fields, creating pairs of electrons and positrons, and slowly leaking them into the interstellar medium. In that light, the AMS-02 positron excess is not a solved dark matter riddle, but a window into the long-term influence of pulsars like Jaminga. The universe has not given up the secret of dark matter yet, but it has offered something else. A clearer view of how much power is hidden in these tiny stellar remnants, and how far their reach extends. Above our heads, a detector the size of a small room counts particles one by one. Among them are positrons that began their journey near the surface of a spinning neutron star, perhaps hundreds of thousands of years ago. They have wandered through the tangled magnetic fields of the Milky Way until a tiny fraction happened to pass through the space our planet occupies now. Some of those particles leave the faintest trace in our instruments. From those traces, we reconstruct halos we cannot see, winds we cannot feel, and beams that never cross our eyes. We learn that Jaminga, once a nameless gamma-ray haze, is not only a quiet pulsar, not only a pair of X-ray tails, but also a vast, invisible cloud of high-energy particles surrounding it like a soft, extended aura. The night sky above may look still, a simple pattern of stars, but wrapped around that pattern is a deeper, hidden structure. Streams of particles, shells of gas, magnetic arcs, and halos of gamma rays. Pulsars sit inside this structure like tiny hearts, beating out radio pulses and gamma flashes, quietly pumping energy into the space around them. And every so often, one of those hearts lines up just right with Earth, letting us listen to its rhythm and understand a little more of the story it has been telling all along. Almost everything we now know about pulsars began with one pair of careful hands noticing something that did not quite fit. In 1967, a graduate student named Jocelyn Bell was poring over long rolls of chart paper from a new radio telescope when she saw a signal that kept returning, over and over, as steadily as a heartbeat. At first, the idea that it might be a message from another civilization was not entirely dismissed. The pulses were that regular, that uncanny. The signal was jokingly labeled LGM for Little Green Men. But more observations and more discoveries of similar sources slowly revealed a different truth. These were not transmitters built by anyone. They were the voices of dead stars. In the decades since that first discovery, the number of known pulsars has grown from one mysterious blip to thousands of catalogued objects scattered across our galaxy. Each new pulsar added a tiny detail, a slightly different spin rate, a different magnetic field, a different age, a different environment. Taken together, they taught us that neutron stars are not rare curiosities, but a common, natural endpoint for massive stars. They showed us that space is dotted with these city-sized remnants, each one spinning, beaming, and slowly losing energy in the dark. Jaminga joined this story in a special way. When it was first identified as a gamma-ray pulsar in 1991, it became only the third of its kind, standing alongside the Crab and Vela pulsars. At the time, gamma-ray pulsars were rare jewels in the data, hard to find and harder to understand. Now, thanks largely to NASA's Fermi mission, we know of hundreds more than 300 neutron stars that flash in gamma rays as they turn. The catalog has thickened, the statistics have improved, and yet Jaminga continues to feel like an outlier, a star that gently refuses to behave exactly as expected. It has already helped reshape how we think about radio emission, particle halos, and antimatter in our near-cosmic neighborhood, and it is hard to shake the feeling that it may still have more to teach us if we keep watching. Pulsars have a habit of doing that. They start as an oddity, then gradually become the key to a new way of listening to the universe. If you tune into the cosmos with the right instruments, there is another kind of signal waiting, one that does not arrive as light at all. It is sometimes called a hum, though there is no air in space to carry sound. This hum is made of gravitational waves, tiny ripples in the fabric of space-time itself, stretching and squeezing distances as they pass. Unlike light, which bounces off matter and can be blocked or scattered, gravitational waves move almost unhindered through everything, carrying information from places that light can never reach. We already know one famous background signal that fills the universe: the cosmic microwave background, the faint afterglow of the Big Bang. It is a bath of microwave light, coming to us from every direction, the cooled remnant of a much hotter, earlier time. When it was discovered in the 1960 seconds, it became one of the strongest pieces of evidence that our universe had a hot, dense beginning. But this light, as ancient as it is, does not reach all the way back to the universe's first moments. It was released about 380,000 to 400,000 years after the Big Bang, when the cosmos had already had time to expand and cool. Before that moment, the universe was filled with a thick, bright plasma, a soup of electrons and protons so hot and energetic that they could not settle down into neutral atoms. In that state, light could not travel freely. Photons kept scattering off charged particles, constantly absorbed and re-emitted, trapped in a kind of cosmic fog. Only when the universe cooled enough for hydrogen and helium atoms to form did space become transparent to light, and the microwave background began its long journey toward us. If we want to look back earlier than that, light will not help us. We need a different messenger, one that does not care whether the universe is transparent or opaque. Gravitational waves are just such a messenger, because they are distortions of space-time itself, and not particles trying to slip past charged matter. They can move through that early plasma almost as easily as they move through the near vacuum of today. In principle, a background of gravitational waves could carry information from the first fractions of a second after the Big Bang moments, forever hidden from ordinary telescopes. Astronomers and physicists have been dreaming about such a background for a long time. The challenge is that gravitational waves come in many pitches, just like sound, and each kind of detector can listen only to a certain range. Instruments such as LIGO on Earth are tuned to higher frequencies. The quick, sharp waves produced when compact objects like stellar mass black holes or neutron stars spiral together and collide. As those binaries whip around faster and faster, completing hundreds of orbits per second just before merging, they send out a burst of high-frequency gravitational radiation. LIGO is exquisitely sensitive to those brief, ringing events. But the universe also produces slower, deeper waves, with periods measured not in milliseconds, but in years. These ultra-low frequency waves are generated by much larger systems, pairs of supermassive black holes, each millions or billions of times more massive than the Sun, orbiting one another at the centers of merging galaxies. Their dance is vast and slow. As they circle, they gently stir space-time, sending out a low, steady signal, a rumbling rather than a crash. Those signals fall in the nanohertz range, frequencies so low that one full wave might take years to pass. LIGO and similar detectors, with their relatively short arms and ground-based limitations, are deaf to such long waves. From their perspective, the slow stretching and squeezing is almost constant, impossible to distinguish from the background. It is as if you tried to detect the rise and fall of the tide using a tuning fork tuned only for bird songs. Yet these slow waves carry rich information. They tell us about how galaxies grow and merge, how often supermassive black hole pairs form and tighten their orbits, and how the large-scale structure of the universe evolves. And layered on top of those astrophysical sources could be something even older: primordial gravitational waves, relic ripples from the universe's birth, stretched to ultra-low frequencies by the ongoing expansion of space-time. Together, all these contributions blend into what is called a stochastic gravitational wave background, a kind of faint, random-sounding hiss that comes not from one loud source, but from countless weak ones added together. The question, then, is how to listen for a hum that slow and that subtle. Building an enormous version of LIGO, with arms light-years long, is not practical. Instead, astronomers have learned to use something nature already provides: pulsars. A pulsar, with its regular flashes, is almost like a clock placed far out in the galaxy. Each time it spins, a pulse of radiation sweeps past Earth. Under normal circumstances, those pulses arrive with remarkable regularity, especially for millisecond pulsars, the ones spinning hundreds of times per second, whose timing can rival or surpass the best atomic clocks. If space-time between us and the pulsar is gently stretched or squeezed by a passing gravitational wave, the time it takes for the pulses to travel changes just a little. The pulses arrive a bit earlier or a bit later than they otherwise would. On its own, a tiny irregularity in one pulsar's timing could have many explanations. Slight changes in the pulsar itself, noise in our instruments, effects of interstellar plasma. But if you listen to a whole array of pulsars scattered across the sky, looking for correlated patterns in their timing, you can start to pick out the unique signature of gravitational waves flowing through the galaxy. This technique turns the Milky Way into a gigantic detector, with pulsars as the endpoints of its arms and radio telescopes on Earth as the readout. Over the past 15 years or so, several collaborations have been timing dozens of millisecond pulsars with exquisite care. One of them, known as Nanograv, has used observatories across North America to build up a long dataset, watching how the tick-tock of these distant neutron stars drifts over time. In 2023, after analyzing more than a decade of data, the team reported evidence for a common, low-frequency signal affecting many pulsars at once, a subtle, shared wobble in their rhythms. The pattern of that wobble matches what you would expect from a background of nanohertz gravitational waves. It is not a sharp detection of one binary black hole, but the first clear sign that the slow rumble of many such systems, and perhaps even the whispers of primordial waves, is reaching us. The signal is still being studied and refined, and other teams around the world are comparing their results. But for many researchers, it already feels like listening to the universe clear its throat before beginning a long, low song. In a way, the path from Jocelyn Bell's first pulsar to this galactic-scale detector is wonderfully circular. The objects that began as mysterious, possibly artificial beacons, have become some of our most trusted natural instruments. They help us measure distances, test the laws of gravity, map the interstellar medium, and now, perhaps, hear the faint background of gravitational waves that has been ringing through the cosmos since its earliest moments. It is a quiet comfort to think about this on a still night. Somewhere out there, Jaminga is spinning, leaving X-ray tails and a mist of positrons in its wake. Other pulsars are ticking just as steadily, scattered through the spiral arms of our galaxy. Their pulses, born in extreme gravity and dense matter, cross vast expanses of space and arrive at our radio dishes as tiny, regular flickers. Hidden within those flickers, when we line them up and listen closely, we begin to make out another pattern, the deep, slow modulation of space-time itself, shaped by colliding black holes, and perhaps by the universe's own first breath. From one student's careful eye on a strip of paper, to international teams timing neutron stars with nanosecond precision, we have slowly learned to read these patterns. And as we do, the universe that once seemed silent reveals itself to be full of rhythms, fast pulses from spinning stars, soft hums from distant mergers, and a background murmur that may carry the memory of the moment everything began. When people first imagined building a detector for gravitational waves, the idea felt almost impossibly delicate, watching tiny changes in the lengths of tunnels here on Earth, and using them to infer the motion of distant black holes. LIGO turned that dream into something real, using two long, perpendicular arms and lasers bouncing between mirrors to measure ripples in space-time smaller than a proton. When a high-frequency wave passes through, one arm is stretched while the other is squeezed. Then they swap, and by comparing the light returning from both paths, we can see that tiny dance. But for the kind of ultra-slow waves we've been talking about, the ones whose crests are light years apart, no realistic upgrade to LIGO will ever be enough. The basic limitation is written into the waves themselves. A wave's frequency is inversely related to its wavelength. The lower the frequency, the longer the distance between each crest. For nanohertz waves, completing just one cycle takes on the order of 1 billion seconds, decades, in human terms. If you work out the wavelength from that frequency, you find something staggering, about 10 to the power of 17 meters. It's hard to feel what that number means. The distance from Earth to the Sun is around 10 to the 11th meters. A light year, how far light travels in a year, is roughly 10 to the 16th. The gravitational waves we're hunting have wavelengths tens of light years long. They wash through whole star systems at once, lifting and lowering them together like slow tides. No tunnel dug into a planet, no matter how ambitious, could ever span a meaningful fraction of a wave that large. So instead of trying to scale up LIGO with longer physical arms, astronomers chose something more imaginative. They decided to let the universe provide the arms for them. The trick begins with pulsars. These ultra-dense neutron stars spin with remarkable stability, sweeping beams of radiation from their magnetic poles as they turn. Each pulse that reaches Earth is like the tick of a distant clock. Millisecond pulsars, which whirl hundreds of times each second, are especially steady. Their timing is so precise that their pulse arrivals can be predicted to within millionths of a second over many years. In the quiet, they keep time better than most atomic clocks. If space-time between us and a pulsar were perfectly calm, each pulse would arrive right on schedule, once we've accounted for the motion of Earth and the star. But if a long, slow gravitational wave passes through, it stretches and compresses the distance between us ever so slightly. The path the pulses travel becomes just a little longer or shorter. To us, that shows up as small advances or delays in their arrival times. The pulsar itself hasn't changed. The road its light is traveling on has. One pulsar alone cannot tell us whether such a change is due to a gravitational wave or to something more mundane, like variations in the interstellar gas that the radio waves must pass through. But if we watch a whole collection of pulsars scattered across the sky, and we see their clocks all being nudged in a related way, that shared pattern can reveal the presence of a background of waves passing through the galaxy. This is the idea behind a pulsar timing array. Instead of two tunnels at right angles, we use dozens of pulsars at all sorts of angles, each providing a long arm of the detector. Here on Earth, radio telescopes listen patiently, recording when each pulse arrives. Over years and decades, those arrival times build up into an intricate record of how space-time along each path has behaved. The Nanograv collaboration chose 68 especially suitable pulsars for their array. They needed them to be scattered widely across the sky, so that their imaginary arms pointed in many different directions. That way, any large-scale stretching and squeezing of space-time would leave a characteristic pattern in the timing residuals, the tiny differences between when pulses arrive and when we expect them. They also focused on millisecond pulsars, whose rapid rotation and outstanding stability make them exquisite cosmic clocks. With such good timekeepers, even very small disturbances become detectable. Astronomers measure the pulse arrival times again and again, sometimes for more than 15 years, and then look for slow drifts, tiny systematic departures from perfect regularity. Some of those drifts are easy to model and remove. We know Earth moves around the Sun. We know the pulsars are drifting through the galaxy. We know the radio waves are delayed by ionized gas along the line of sight. All of these effects can be calculated and accounted for, like subtracting the steady background noise from a recording. What remains after all that cleaning is a mixture of random noise and, possibly, the signature of gravitational waves. The random part can come from many sources. Small, unpredictable changes in the pulsars themselves, unmodeled fluctuations in interstellar plasma, or subtle quirks in the instruments here on Earth. If we looked at just one pulsar, we could never be sure what we were seeing. But with 68, we can ask a more powerful question. How do the timing fluctuations in one pulsar relate to those in another, depending on how far apart they are on the sky? If there were no gravitational wave background, we'd expect no special pattern at all. The timing noise from different pulsars would be largely uncorrelated. The deviations in one would have nothing to do with those in another, except by coincidence. On a graph of correlation versus angle between pairs of pulsars, the points would simply hover around zero, a flat line, with no particular shape. A universe filled with nanohertz gravitational waves, however, leaves a very particular fingerprint. Because gravitational waves stretch space more along one direction and squish it along the perpendicular, the way they change the distance to a pulsar depends on where that pulsar sits relative to the wave. When we average over many waves coming from all directions, theory predicts a distinct curve for how strongly pairs of pulsars should be correlated as a function of the angle between them. This pattern is called the Helling-Downs curve. Close pairs of pulsars should show one kind of shared behavior. Pairs at right angles should show another. Pairs almost opposite each other on the sky should be correlated in a different way again. The exact shape of the curve is like a quiet signature of the gravitational wave background, something you can't see in any single pulsar, but that emerges when you step back and look at them all together. That is what Nanograv set out to find. Over more than 15 years, they gathered pulse arrival times from their 68 millisecond pulsars, using radio telescopes to listen in the same steady way, night after night, year after year. Then they modeled and subtracted everything they could think of that might mimic or obscure a signal. Finally, they compared the tiny residual fluctuations from each pulsar to those from every other pulsar, asking, how do you dance together on the sky? On the 28th of June, 2023, they shared the answer they had found. The correlations did not line up along a flat line. Instead, they traced out a shape very much like the predicted Helling-Downs curve. The error bars, those little vertical lines showing the uncertainties in each point, are still large, and the data is not yet perfect. But statistically, the match is strong enough that the odds of it being a chance accident are about 1 in 1,000. In physicists' language, that is a 3 sigma result. Not yet the gold standard of a formal discovery, which usually demands 5 sigma but solid, compelling evidence. In simple terms, the pulsars are not ticking independently. Their clocks are being nudged in a subtly coordinated way, as if they are all floating in the same very gentle, very slow swell of space-time. The galaxy-sized detector we built from their pulses is responding to something real. We still do not know, in detail, what makes up the hum that Nanograv has begun to hear. The most likely contributors are vast pairs of supermassive black holes, orbiting in the centers of galaxies that have merged and merged again over cosmic time. Each pair adds its own quiet note to the background, and together they form the low-frequency chorus washing through the Milky Way. Woven into that chorus might also be the stretched-out remnants of gravitational waves from the universe's infancy, though teasing out that component will be much harder. For now, the background is like the murmur of a crowded room, heard from far away, full of information, but not yet resolved into individual voices. As the observations continue, and as more pulsars are added to the timing arrays around the world, the error bars will shrink. The pattern will become clearer. Subtle features in the spectrum of the background, the way its strength changes with frequency, may reveal whether massive black hole pairs, cosmic strings, or primordial processes dominate the signal. And somewhere in all of that, we may eventually be able to pick out the song of a particular system. A pair of supermassive black holes slowly circling one another, their gravitational waves imprinting a tiny, regular modulation on the timing of many pulsars at once. With that, we would not just be hearing the collective roar of countless distant events, but following the rhythm of individual giants as they move toward eventual union. Until then, the image is already beautiful, a galaxy full of spinning neutron stars, each one a lighthouse and a clock, scattered across tens of thousands of light years. Their pulses travel through a sea of space-time that is never completely still. Here, on our small world, we gather those pulses with patient, listening dishes and compare them with one another, looking for the faintest shared sway. Out of that long, quiet watching comes the realization that Earth, the pulsars, and everything between are gently bobbing together on the same invisible waves. A reminder that even the stillness of the night is part of a much larger motion. By this point in our wandering through neutron stars and gravitational waves, it might feel as though the universe has already shown us plenty of strange things. And yet, tucked into the night sky, there is another kind of mystery. Sudden, brilliant blue flashes that appear without warning and fade almost as quickly as they arrive. Astronomers call them luminous fast blue optical transients, LFBOTs. The name is descriptive rather than poetic. They are luminous because they rank among the brightest explosions we have ever recorded. They are fast because their light climbs to a peak and then drops again in just days. They are blue because most of their glow lies at short wavelengths, where very hot processes tend to shine. And they are optical transients because, like the flash of a camera, they flare briefly in visible light and then vanish. The first known LFBOT was seen in June 2018 by a survey telescope in Hawaii that normally spends its nights watching for asteroids. In a routine scan, it noticed a new point of light in Hercules that had not been there before. Within a few days, that point brightened to a level roughly 100 times greater than a typical supernova, even though it lay about 180 million light-years away. And then it began to fade. Its official catalog name ended in cow, and the community quickly adopted that as its nickname. At first, astronomers tried to fit the cow into the comfortable framework of a core collapse supernova, the death of a very massive star whose core can no longer support its own gravity. Its spectrum looked roughly similar to that type of event, so, tentatively, it was filed that way. But as more telescopes joined the observations, the cow's behavior began to tug against that label. It rose to its peak far faster than a normal supernova and faded away just as quickly. Its brightness was 10 to 100 times that of many well-studied explosions. The details of its spectrum, the shapes and widths of its emission lines, didn't line up cleanly with any familiar subclass. And when researchers modeled the geometry of the blast, it appeared strongly lopsided, with energy and matter pouring out more in some directions than others. Supernovae can be messy, but this was something else. When one object refuses to fit, ideas proliferate. Some scientists suggested that the cow might be a star, torn apart as it wandered too close to a black hole, its gas stripped off and heated until it shone. Others imagined a massive star collapsing in such a way that it instantly formed a central black hole or neutron star, with that compact remnant driving an extra surge of energy into the ejector. Each scenario explained part of what was seen and left other details out of place. It didn't help that, for a while, the cow stood alone. With only one example, It was hard to know whether we were seeing a unique oddity or the first member of a hidden family. That changed within months. Later, in 2018, and again in 2020, astronomers found similar, bright, fast, blue flashes. Following the playful habit sparked by the cow, they nicknamed these newcomers the koala, the camel, and so on. With 3 or 4 cases to compare, the sense of a pattern began to emerge. This was not just a single strange supernova, it was something larger. When the properties of these early LFBOTs were lined up, one shared feature stood out: their homes. All of them were traced back to the spiral arms of their host galaxies, the curved bands where gas clouds are dense and new stars are being born. Massive stars, those destined for core collapse supernovae, live fast and die young. They do not stray far from their birthplaces. Seeing each of these fierce blue flashes in a spiral arm fit neatly with the idea that LFBOTs were tied to the deaths of such stars, perhaps in an especially energetic or asymmetric way. Just as that picture was starting to feel plausible, a new event arrived to complicate it. In 2022, a wide-field camera in California spotted another explosion, with all the usual signatures of an LFBOT: intensely blue, extraordinarily bright, and fast. But after the initial flare, this one refused to fade quietly. Instead, it began to stutter. Over the course of minutes and hours, the object, soon nicknamed the Tasmanian Devil, produced multiple short bursts of light, each one nearly as bright as the original flash. Rather than a single clean peak followed by a smooth decline, its light curve looked like a series of jolts. Calculations suggested that, taken together, these pulses released more energy than hundreds of billions of suns, compressed into brief, repeated flickers. Strange behavior always invites careful checking. Could this pattern have come from an instrument problem, a software error, a miscalibration? In this case, the answer seems to be no. More than a dozen telescopes around the world observed the same sequence of pulses. The Tasmanian Devil was not a glitch. The sky itself was doing something we had not quite seen before. Even so, imaginative versions of the core collapse story could still be stretched to cover it. Perhaps, in some rare deaths of massive stars, a newborn neutron star or black hole goes through spasms of activity, gulping down infalling matter in clumps and releasing energy in repeated bursts. The theory creaked, but it did not break. There was still room to believe that LFBOTs, wild as they seemed, were all exotic kinds of stellar explosions. Then, in April 2023, another bright, fast, blue event appeared, and this one tugged at the picture from a different angle. Its nickname, drawn from its catalog name, became the Finch. In its colors and timing, the Finch looked very much like the earlier LFBOTs, but it lived in a very different neighborhood. Instead of being nestled in a busy spiral arm, the Finch flared about 3 billion light-years from Earth, in a patch of space roughly 15,000 light-years away from the nearest obvious galaxy. On the images, it sat between galaxies, out in the dim outskirts, where the sky is mostly empty. For something thought to come from the death of a short-lived, massive star, this was awkward. Such stars do not usually have time to wander so far from star-forming regions. That one detail forced astronomers to take a step back and ask more open questions. If LFBOTs are not always tied to young, massive stars in spiral arms, what else could make such brilliant, brief, blue flashes? One possibility is that some of them, especially outliers like the Finch, are not ordinary explosions at all, but stars being torn apart by intermediate mass black holes. We know of stellar mass black holes and of supermassive black holes at galaxy centers. Between them, in the range of 100 to perhaps 10,000 solar masses, lies a missing middle, objects we have long suspected but not yet proved. If such black holes exist, a natural place for them to hide would be in dense globular clusters, those spherical swarms of old stars that orbit far out in a galaxy's halo. In a cluster like that, a central black hole might occasionally trap a passing star. The star could circle closer and closer, stretched by tides each time it swings past, losing material that spirals inward and heats to extreme temperatures. Some of that matter might be flung out at high speed. The flare from such an encounter could be bright, blue, and short-lived, very much like an LF-bot. If the Finch sits in a faint globular cluster too dim to see with current images, its apparent loneliness between galaxies would make more sense. Astronomers hope that more sensitive observations, especially with instruments like the James Webb Space Telescope, will be able to probe the Finch's surroundings deeply enough to reveal or rule out such a hidden cluster. A glimpse of a faint knot of ancient stars at its position would tilt the balance toward the intermediate mass black hole idea. A second possibility turns back to neutron stars. When two neutron stars orbit one another in a tight pair, they slowly spiral inward as they lose energy to gravitational waves. Eventually, they collide in a kilonova, a brief, extremely bright burst that can forge heavy elements and send ripples through space-time. These binaries can be kicked out of their home galaxies by earlier supernova explosions and then drift through the galactic halo or into the spaces between galaxies before merging. A kilonova between galaxies would look very much like an isolated flash, just as the Finch does. One of the clear hallmarks of such an event would be a chirp of gravitational waves, a rising tone as the two stars whirl faster and faster before impact. But when the Finch went off, detectors like LIGO happened to be offline for upgrades. There is simply no data to tell us whether space-time itself rang at the same time. No strong gamma-ray burst was recorded either, but at a distance of 3 billion light-years, even a powerful signal might have been too faint or pointed in a different direction. For now, the neutron-star merger idea remains plausible but unproven, sitting beside the intermediate mass black hole picture as one more story that might fit. And so, luminous, fast blue optical transients remain in that in-between place where ideas multiply faster than answers. The cow, the koala, the camel, the Tasmanian devil, the Finch, and a few quieter cousins together mark out a new corner of the transient sky. Explosions that are blue, fast, extraordinarily bright, and sometimes strangely placed. They hint at violent encounters with black holes or neutron stars, but they refuse to settle on one clean explanation. What astronomers can do in the middle of that uncertainty is simply keep watching. Wide-field surveys like the Hawaiian Atlas system and the Zwicky Transient Facility in California already sweep huge areas of the sky every night, catching brief flashes that would otherwise be missed. In the near future, the Vera C. Rubin Observatory in Chile will join them, photographing the entire southern sky again and again, and gathering more light than any survey before it. Each new image will be another chance to catch a fresh LF-bot in the act. When one appears, telescopes across the spectrum swing into place. Optical instruments measure how its brightness rises and falls. Spectrographs read the fine structure of its light to infer speed, composition, and temperature. X-ray and radio observatories look for afterglows and jets. infrared eyes search for faint host galaxies or star clusters hiding in the dark. Slowly, from these many angles, a clearer picture will grow. For now, though, LFBOTs are still more question than answer. Their light curves are plotted carefully, their locations catalogued, their spectra archived, but the story behind them remains softly unfinished, in a way that is part of their quiet charm. They remind us that even now, with sensitive instruments perched on mountaintops and circling Earth, the sky can still do something that makes experienced observers stop, look again, and admit, we don't know yet. Somewhere out there, perhaps in a crowded spiral arm or drifting between galaxies in a halo cluster, another such flash is waiting to happen. When it does, its light will travel for millions or billions of years before washing gently across our detectors for a few nights. Then it will fade, leaving us with numbers, plots, and, most of all, the space in which new ideas can grow. In that space, patient, curious, unhurried, we keep listening, knowing that each brief blaze is both a puzzle and a promise that the universe still has more to show.